for my part of the hardware afternoon, and I will give a bit of a more practical, tutorial style introduction with some time at the end to do a bit of exploration by yourself with our tool HANA. Our tool HANA is developed by me and by my colleague Moritz, who's also here for the whole week. And yeah, we're both researchers slash PhD students at Oliver's group, and developing our NAS tooling. In my case, I'm also quite involved in the deployment and the actual chip design. But that's what we're doing. And where we're coming from is our first publication on hardware accelerator and neural network co-optimization. That's the original publication. And in that case, in that publication, we did the whole optimization for a very specific use case, ultra-low power audio processing devices, and using a very specialized hardware accelerator architecture. And since then, we're mostly concerned on how we can develop our toolchain further so that we can support the same toolchain, but for different hardware backends. So our core neural architecture search framework now consists of a hierarchical neural network search space description. Some maybe more interesting expression and constraint system to reduce the size of the explored space of neural networks. Then some generic ML-based performance prediction algorithms and some pretty standard search algorithms for doing neural network architecture search. The neural network architecture search component is then used in the framework to configure the training, for example, the quantization-aware training, the data augmentation, the deployment toolchain, and then finally also different hardware backends depending on which need arises. Most of our current work has been going into the actual search space descriptions, and as you will see, we first describe our search spaces as pretty much as by directly describing a neural network computation graph that can be written down in Python, really pretty similar to these descriptions on the right, and we describe the graph on the left. To describe architectural choices, we also add a choice operator, or can add a choice operator to the neural architecture graphs, which represent different choices to take in the architectural path, in the path of the architectural of the neural network architecture. Blocks represent reusable components, and blocks are just defined by defining a function in the neural network architecture description. Blocks on the neural network graph level are only conceptual, so we always represent the full graph and just represent the blocks in the final graph by the names or the IDs that we give to the different nodes. That are the search space descriptions, and this search space descriptions are augmented by an expression and constraint system. The expression and constraint system is used to describe and limit the choices for parameters in the operators of our computational graph. So for example, the simplest constraint that we can derive from a neural network topology, the number of input channels for a neural network, the number of output channels of a convolutional layer needs to be the same as the number of input channels in the next layer. That's the most basic forms of constraints, but we also transform the other derived symbolic expressions for other kinds of, for example, shapes of the neural network architecture graph. And then these can, for example, be augmented to describe that, for example, the strides on both sides of an addition of the additions need to be the same, or even if we have one single layer at this side of the neural network graph, and here a stack of layers, that in the end the shapes must match, so derive any architecture that fulfills this invariant. To do that, we can, for example, extract the shape of the input and the output of such a stack of neural network layers, then calculate from the differences in spatial dimensions the strides or the effective stride of the whole stack of neural network architecture layers, and then set the layer on the residual link to also evaluate or use this effective stride on the network. Constraints can also derive for a whole other lot of parts of the neural network architecture graph. For example, the number of multiplier accumulates, the number of parameters, the total amount of downsampling the whole neural network does, and so on. They are all evaluated symbolically, so they are faster to evaluate than even building the model and then traverse, for example, a PyTorch graph or something like that. And we can use tools like constraint solvers to directly find suitable models for a target architecture. And we can also directly integrate external information, for example, from a target hardware description. So we can put in directly hardware constraints like my target hardware only supports convolutions up to a particular size, or convolutions always need to be of quadratic filter size or something like that. Yeah, and then before we get into the practical part, we also wanted to quickly present our performance prediction or generalized performance prediction method that we use as the surrogates for target measurements or other costly evaluations, which are always, in our case, always done using a graph convolutional neural network to extract an embedding of the neural network architecture, and then we use some regression head to predict the actual neural network metrics. That's the quick introduction into our toolchain. And now we have prepared some basic hands-on tutorial style introduction with our toolchain. So have a lot of fun. And yeah, I think I'll then do a wrap up at, I think, 10 minutes before 4. I hope you had some fun with our tooling to see a bit, the directions where we are currently developing. So our search space descriptions, and then the actual neural network architecture search tooling, allowing an easy integration of different hardware performance estimators, and then also the little bit at the end as a take-home message that multiply accumulate units are not that good a proxy for actual target performance. Yeah. So where to go from here? Do you have any questions or remarks? I don't see any. So then just to conclude from my side, for me, this week has been quite valuable, especially when considering the target directions where I will take our neural architecture search tooling next. And I hope you had some fun with our tooling, and if you are having any problem running or finding a suitable neural network for embedded hardware, please feel free to contact us at any point in time. So thank you, and see you in the break.